We're very happy today to have Cezary Cieśliński. Again, apologies for my mispronunciation of Polish. I've been practicing.
Oh, that was perfect.
Okay. Who is here to talk about the principle of disjunctive correctness based on work with Matusz Warwick and Bartek Cieśło, who have been here the last couple of weeks. So we're very excited for this talk from you. So go ahead.
Thank you very much. So the topic will be disjunctive correctness, or more generally, I will speak about truth theories. Before I go to disjunctive correctness, I want to introduce some background. So the first thing, theories CT minus and CT. CT is for compositional truth. It's a classical axiomatic truth theory. So we have the usual condition for the truth of atomic expressions, and then the axiom stating the truth commutes with connectives and quantifiers. I added also the axiom stating that only arithmetical sentences are true, as this permits to simplify the formulation of some results. Just a couple of things here. CT minus means that we do not have extended induction. Extended induction, I will use this expression for induction for formulas of the language with the truth predicate. So we do not have this in CT minus. CT is the theory with full extended induction. I'm not going to read the axioms, but I will want to comment just on one axiom, namely the axiom for the quantifier. I want to emphasize that this version of the axiom employs numerals. This will be somewhat important later. So we have the truth of a general statement. A general statement is true if and only if every instantiation by a numeral is true. In the literature, there is an alternative formulation. Formulation referring to using closed terms. So this would be a general statement is true if and only if every instantiation by a closed term is true. I will refer to these two versions as numeral variant of CT minus and term variant of CT minus. The difference between the two is negligible if we have the sufficient amount of extended induction, because by extended induction we can show that both versions are the same. Yeah. However, my context, my setting here will be either non-inductive or weakly inductive theorems. This should not be taken for granted in such a setting that these variants are equivalent. Okay, I will emphasize this point later when it becomes important. Then basic properties, just a quick overview. So the definition here is the definition of syntactic conservativity. So we can ask the question whether a given theory of truth is syntactically conservative over its base theory. Well, in my case, base theory is Peano arithmetic. So it is conservative if for every arithmetical sentence, if the truth theory proves this sentence, then already Peano arithmetic can prove this sentence. Then observation that CT with full induction is not conservative. It proves global reflection for Peano arithmetic. This is like a folklore observation, I think. Everybody seems to know it. The proof is very easy. Just a very natural argument. We can prove that all the axioms of PA are true, and that truth is closed under say modus ponens. It's our rule of inference. But in contrast, CT minus without the extended induction is conservative over Peano arithmetic, and here I have given the classical source Kotlarski, Krajewski, and Pachman, but at the moment we are in a rather comfortable situation because there are several proofs in the literature of this important theorem, and these proofs they employ various techniques, so it can be to everyone's taste. So what I mean, there is a proof of Enayat and Visser, which employs classical model theoretic techniques. Basically, this is the what is employed is the union of elementary chain of models argument and theorem compactness. Yeah. So this is the argument, the proof, which will be to the liking of those who favor model theory. But also there are proofs which are proof theoretic. So also this is accessible from this angle. In particular, there are two proofs. One is a proof by Graham Lee, which the proof uses cut elimination. And there is also recent. There is also my proof, also in terms of cut elimination, but different from Graham's proof. So whether you love model theory or proof theory, there is a proof. You can find the proof to your liking. Now, what we do, our group in Warsaw, one of the avenues of research is what we call Persky boundary program. So in this program, the general question is which truth axioms are responsible for the transition from conservative to non-conservative extensions of the base theory. And the line, this line is called Persky boundary, and there are concrete problems still open in this area. These problems concern systems with weak induction, non-inductive systems with collection principle, non-inductive systems with axiom guaranteeing some version of propositional soundness of truth. Some of these problems, they will be formulated and described in this talk, at least that's the plan. Weakly inductive, well, weakly or not so very weakly, in general, CTN obtained from CT minus by adding induction for formulas of a given level of syntactic complexity. And CT1 already is not conservative. And there is also a theorem due to Mateusz Wełik. The theorem states that CT0, so the theory with delta zero induction for the extended language, already this theory is not conservative, it proves global reflection. Just to comment, two comments here. The first one is that this is not so easy to show. It's not an argument like just a couple of lines. It's not my aim to describe the proof. Let me only mention, like in passing, what's the basic difficulty here. So let's say that we are trying to prove global reflection in a direct manner, like we want to demonstrate that all the axioms of PA are true, and we want to demonstrate that truth is closed under, say, modus ponens. So some parts are easy. Showing that truth is closed under modus ponens is completely unproblematic by delta zero induction. It is also unproblematic to demonstrate that all arithmetical axioms of Peano arithmetic are true, at least if we formulate Peano arithmetic as a theory with parameter-free induction, which we can do. The problem is, the difficult part is about logical axioms. If we have modus ponens as the only rule of inference, and with modus ponens, closure under proofs goes smoothly, then the set of axioms will be closed under generalization. So if phi is an axiom, is a logical axiom, then an arbitrary result of preceding phi with a block of universal quantifiers, no matter how long, is also a logical axiom. And the not so straightforward part is exactly here. The question is how, so to speak, how to swallow this block of universal quantifiers by delta zero induction. So it takes some work. The second remark here at the bottom, this result, non-conservativity of CT0, what we have at the moment is the information that this is so for the numeral version of CT0. So if the quantifier axiom employs numerals. So far, we haven't found a way to modify Mateusz's proof in such a way as to work for a term variant of CT. So at the moment, well, I would say it's one of the open problems. Yeah, how strong is delta zero induction? The quantifier axiom is formulated in its term variant. We don't know. Okay. Still setting up the state, I want just to list some results. So this formula, the intuitive meaning of this formula is that X has a proof from true premises. And the second formula, the reading is that X has a purely propositional proof from true premises. So the first one is like X follows from true premises in full first order logic, and the second X follows from true premises in propositional logic. So these two formulas. And now there is a theorem stating that the following axiomatizations, the axiomatizations listed below, that they are axiomatizations of one and the same theory, equivalent axiomatization, axiomatizations. So the first one, I will not read CT minus Q, that's all the time, yeah, that's what is added. The first one, logic is true. Yeah, whatever is provable in pure logic is true. The second is global reflection for Peano arithmetic. All theorems of Peano arithmetic are true. The third, C, truth is closed under first order logic. Whatever is provable from true premises is true. Then the next one, truth is closed under propositional logic. Whatever propositionally follows from true premises is true, and the last one is CT0, delta zero induction. So all of these are axiomatizations of delta zero induction. In this talk, I will really use at some point that one. This information that closure of truth under propositional logic is that it is delta zero induction. Okay, I gave some references below, but I will not read it. Now, getting closer to my topic, long disjunctions. So S be a sequence of arithmetical sentences, called a sequence in a model M. Yeah. Then we can form the disjunction of sentences belonging to S. I will use either this or this notation in the length of the sequence C. And I'm adopting the assumption about bracketing. So the assumption is this. The assumption is that bracketing is to the left. Yeah. So in fact, maybe let's start from here. When you have such a formula, the assumption is always that it looks like that with this bracketing. Yeah. So the last disjunct is very sorry. Very near in the syntactic tree of this, very close in the syntactic tree of this formula. So in effect, such a disjunction, when we have it, we have first this disjunction and then the last disjunct, 5 plus 1. And now, principles of disjunctive correctness. DC stands for disjunctive correctness. It's a generalization of the compositional axiom for disjunction. The compositional axiom concerns just a disjunction of two sentences. And here we've got generalization. So disjunction, no matter how long, yeah, non-standardly long, disjunction is true if and only if at least one of the disjuncts is true. And then we have weakenings of this principle. Disjunctive correctness, here we've got biconditional, and these weakenings are simply two implications. Yeah. So we have disjunction introduction. I think that was how I called this in the abstract. Sorry, I use a different notation here. So this is disjunction introduction. If one of these sentences from the sequence is true, then the whole disjunction over the sequence is true. So we can introduce this disjunction. And DC out or disjunction elimination. If a disjunction is true, then we can go to one element. And there is a theorem due to Ali Enayat and Fyodor Pahomov. It's published paper, which contains a proof of the theorem that adding this principle, disjunctive correctness, to CT minus produces CT0. So DC is not conservative. A surprising result, unexpected. So something like that, just you would think like generalization of the axiom for disjunction produces already non-conservativity delta zero induction. And my aim here is to show how to improve on this result. The improvement will be twofold. Firstly, what I'm going to present is a simpler proof than the one originally given by Enayat and Pachomov. I think it's a nicer proof, and I think that I can say it safely because one of the authors, Ali Enayat, he says himself that this proof is nicer, so I'm on the safe side. And secondly, I will want to prove a stronger result, namely, Enayat and Pachomov's result, it left open the question of the strength of these two principles separately. So they proved that adding this biconditional produces non-conservative extension, but the question was, how about these two implications? What I will show that already DC out by itself produces non-conservative extension. DC out already is equivalent to delta zero induction. Well, I will not show this, but there is also the result in our paper that DC in is conservative. So that's the final picture. DC in is conservative, DC out is not. And in order to do this, I introduce just two additional notions.
Cezary, can I ask a question at this point? It's about the theorem. So if one thinks in terms of expansions with such, those truth predicates of a model of a non-standard model of PA. So if you have one that is a full satisfaction class, but is does not satisfy delta zero induction, then it means that it must happen because there is some case of this disjunction correctness that goes wrong, right? Mm-hmm. So there is a guarantee that if you have one that's not delta zero inductive, there's something. So but delta zero induction in a model of arithmetic is equivalent to set being a class or being piecewise defined. Yeah. So it means that if you have, so that does it also mean that you have a satisfaction class that's it's piecewise defined up to a certain level, but then fails to be piecewise defined above it. Then this instant, how long is the shortest instance of a disjunction, that correctness that fails? Is it something that's visible in the proof? No, sorry, I haven't thought about, so it's just these terms. Right. You can sort of define like disjunctive correctness up to a certain initial segment I. Okay, and then does it mean that that also it implies some kind of piecewise definability up to a certain level? But this hasn't been. This is not something you can see instantly in the proofs that you do. Possibly not. So I mean, I'm planning to show you really the proof. So we'll see. Yeah. Okay. Thank you. Okay. So just two notions.
which I call sequential induction and sequential order induction. Just induction on the elements of a sequence. The first principle, S. Let's say that S is a sequence of arithmetical sentences. And this principle states simply that if the first element of the sequence is true, and with each element the next is true, then all elements of the sequence are true. And the second principle, sequential order induction, it's like a course of values recursion. Yeah. If for every j from the truth of all elements up to j without j, the truth of the j follows, then all elements of the sequence are true. Okay, these principles, they are closely related to delta zero induction, as will be seen in what follows. And now my aim, this will be my aim, to demonstrate non-conservativity of the Cout. And here is just a map how this will play out. The first step, I will show that adding the Cout permits us to prove sequential induction. Yep. Then I will observe that sequential induction permits us to prove DCing. In effect, this means that if we add DC out, we are already in full disjunctive correctness. Yeah, adding DC out gives us also full DC. Then, in the next step, there will be an observation that sequential order induction is simply zero. It's the same as delta zero induction. And finally, we will have the observation that adding full DC, full disjunctive correctness, gives us sequential order induction. So if we put this together, it follows that DC out and CT0 are the same. So I will show this step by step, but let me emphasize that the crucial part is here. So we'll really start from the crucial part. To prove this, there will be some, let's say, trick. And all the other parts are rather straightforward. They involve no tricks. Well, in some cases, there are corollaries to what is in the literature. So step by step. And I will be moving towards this here, any sequential induction from this out. And this part employs, it is really based, the idea is based on Yablo's paradox. Yablo's paradox, just very quickly, a reminder. Universal version, existential version. In the universal version, we consider a sequence of that of them states all the sentences, so that each sentence states there is a guy later in the sequence, which is false. And both situations generate a contraction. What follows, the reasoning to be presented in the moment is based on existential version. The only difference is that here we have the assumption that there is a guy appearing later in the sequence, which is false. And I will have there is a guy appearing earlier in the sequence. It's false, but the sequences will be like non-standard. So we'll have also an infinity downwards. Okay, so now details. So the theorem is that if you add DC out, sequential induction can be proved. So let's fix a sequence of sentences and let's assume that the first element is true, and let's assume that the truth of each element entails truth of the next element. And now we run Yablo. So I construct a sequence of sentences, phi 0, phi 1, and so on, up to C plus 1. Phi 0 is, well, something, just to start, 0 equals 0, it's trivial true. Then, on the level A plus 1, just look what are we saying. This is an implication, and the sequence here states fact. As in existential version of Yablo's paradox, the consequent states at least one of the guys drink earlier, one of those phi k's or phi i's, false. But we are doing this in terms of a big disjunction. Yeah, it's not an existential quantifier, it's a big disjunction. And we make it conditional upon the falsity of alpha k. So if alpha k is false, so to speak, then Yablo. Yeah, that's the idea. And the proof will be finished by showing these two things. So firstly, for all k smaller than equal C plus 1, phi k is true. So all these phi k's are true. That's the first part. In the second part, we are proving sequential induction. So we are proving that all these alpha sentences are true. If one of them, alpha k, is false, then below k there is a number j such that phi j is false. Clearly, from those two follows that all sentences in the sequence are true. Because if some of them is false, then one of the five formulas, 5 sentences is false, but all of them are true. Yeah, following the two is the proof. Okay, so claim, the first claim, all of the phi k's are true. Yeah, so the proof runs like this. Assume that it's not. Yeah, assume that phi k is false. Then k is larger than 0 because step 0 was triviality. Hence, it's an implication. In order for this to be false, the antecedent of the implication must be true, and the consequent must be false. And then we just spell out the consequent. What is this? Disjunction. There are two disjuncts. The first disjunct is a disjunction below k, and the second disjunct is the negation of phi k. So just by compositional axioms, we obtain that both disjuncts must be false, hence phi k must be true. But phi k is this implication, yeah, by definition. and we have not alpha k. By our assumption, because we assumed that if a given alpha in the sequence is true, then the next is true. It was one of our assumptions. So with not alpha k, then not alpha k minus 1. So by the truth of phi k, we obtain this, well, which is a contradiction. Yeah, here. So this ends the proof of the first part. All of them are true. All phi k's are true. And this will be really quick. If one of the alphas is false, then one of the phi sentences must be also false. Yeah. So assume that alpha k is false, and now we already know that all phi k's are true. So in particular, phi k plus 1 is true. But phi k plus 1 looks like that. It's an implication. Yeah. This is true, and we have the antecedent. Therefore, the disjunction is true, and now we employ this out. Yeah, there is a disjunct. There is a false disjunct, which that was exactly our task to obtain. So this ends the proof. So the main idea is to use this sequence, and I don't know, if you haven't seen the original Enaya Pahomov argument, then take my word, it's much simpler than what they did. And now let's go through the rest. The next observation, sequential induction permits us to prove DC in. We already know, this was the previous theorem, that DC out proves sequential induction. So the moral, the outcome is that DC out and DC, they are equivalent over CT. DC out entails full DC. And this is a rather quick argument. We work with sequential induction. We fix a sequence of sentences and suppose that one of these guys is true, and the claim is the whole disjunction over the sequence is then true. So the first observation is that if alpha j is true, then the disjunction up to alpha j is true because it has this form. Then we have the second disjunct is true, and the truth of this is guaranteed by a compositional axiom for disjunction. But so far, we have let's say a part of this only, because it's up to today, yeah, which is true. And what about the rest? It's simply that the disjunction up to k is true. The disjunction of up to k plus 1 is also true. Hence, we can use sequential induction to reach the final result. So remember, we are working with sequential induction. And then the next observation is just a quick corollary from the literature. That sequential order induction and CT0, that is zero induction, they are one and sequential order induction you prove just by the delta zero induction. And the proof is finished by observing that sequential order induction implies closure of truth under propositional logic. So I'm referring to the result formulated earlier. There is a result, a published result. The closure of truth under central logic is delta zero induction. So it's a very direct argument. So you just fix a proof in propositional logic, proof from through premises, and you use sequential order induction to demonstrate that all the elements of the proof are true. It's quite direct by sequential order induction. Then we observe the next element, that if we have full DC, and remember, we have it as soon as we have DC out. This has already been demonstrated. So DC is enough to prove sequence order induction. So in order to see this, just fix a sequence of formula of arithmetical sentences, and suppose that phi I is true for all it takes a moment. I mean, I omitted this part. To just work out, after working out the details by DC, but both directions are used here, DC in and DC out. You can demonstrate this is prolongable. Negation of a disjunction of negation, like conjunction, but actually we cannot use conjunction here. This is so up to j, then this will be so up to j plus 1. DC in and DC out. And because of this, we can use sequential induction. We are in the course of proving sequential order induction, but we already know that DC out proves sequential induction. By sequential induction, which we can conclude that this holds for each I, and again by disjunctive correctness, this implies that each phi j is true. Okay, I have the question: how long I can speak?
Usually we go up to 10 or 15 minutes after, so you can maybe 20 minutes from now you have it.
Yeah, because there is one. This really completes the proof of the fact that DC out by itself is non-conservative. I wanted to show one more result, but before this, let me come back to the definition of disjunctive correctness. There is something like what you could call a philosophical side to this story. So there is a philosophical discussion focusing on the question, how innocent are the principles of truth? And how innocent has been interpreted as a question about conservativity. So we already, well, we know it's a very familiar fact that that CT with full induction is not conservative, but then some people reacted by saying, okay, CT is not conservative, but CT has full extended induction. Full extended induction, so these people said, full extended induction, it is not a truth principle. It's an arithmetical principle. There is nothing specific about truth here. It's rather about our notion of natural number. Natural numbers are such that whatever set of natural numbers you consider, it is inductive, whether it's definable or not, whatever. This is arithmetic, not it's not a truth theoretic axiom. So here, DC and also by the same token DC out, it looks more like a truth theoretic principle. Disjunction is true. If a disjunction is true, then at least one disjunct is true. Okay, so it was this, and now yeah, so I was here. This was the end of the proof, and now I want to say a few words about a certain open problem. We don't know the answer to the question described here, and next I want to show a result which is motivated by this open problem, although the result does not solve it. Okay, so the problem. Define the theory CT out. Let it be CT minus extended with the axiom all propositional tautologies are true. Yeah, and the question is how strong this theory is. Maybe it's another incarnation of CT0, or maybe not. Maybe it's conservative. We do not know. The motivation for asking this question hopefully is clear by now. Namely, as we've seen, yeah, it transpired that various properties, which you could call propositional properties, are strong. Yeah. So closure of truth under propositional logic. This was the older result, that it's delta zero induction. Disjunctive correctness, DC out even. These are, you could say, simple propositional properties. And for this reason, it looks like a natural question. And we do not know the answer. Maybe let me say, in spite of some rather solid efforts to prove or disprove. This, well, a quick comment, the answer would be negative. What is, oh, if we had a sort of conjunctive correctness, yeah, so given the fact that every phi j is true individually, the conjunction of phi 0 up to phi a is true. Okay, the situation is of conjunction is really dual to that of disjunction. So this would be like conjunction in is the same as disjunction out. Yeah. So we don't know whether this theory is strong enough to prove this. And a result motivated by this question. Sorry, a definition first. Notion of quantifier-free correctness. Yeah, quantifier-free correctness is the following principle. For every phi, which is a quantifier-free arithmetical sentence. So phi is just Boolean combination of closed term equations. Yeah. For every such a phi, phi is true, but true in the sense of arithmetically definable truth predicate. Yeah. So I've used here a truth predicate for delta zero formulas. Actually, we could weaken this. They are quantifier free, so it doesn't matter what happens with the bounded quantifiers. Anyway, phi is true in arithmetically expressible sense, then phi is true in the sense of our T predicate. So, in effect, the principle states that our predicate behaves well for sentences of this restricted class. It is not in conflict with what can be arithmetically expressed. It is known that this is a weak principle. So this principle, quantifier-free correctness, it can be added to CT minus without increasing arithmetical power. Conservative. It's a long way from being non-conservative. Stronger principles can be added. We can have a principle of incorrectness. Yeah. For every phi of syntactic complexity n, phi is true n, arithmetical predicate for sentences of this complexity, then phi is true. You can also add these to CT minus conservatively. More than that, you can add this not just for a concrete n, you can add this for all n's. Yeah, so you can add an infinite set of such correctness principles for all natural numbers n, and this is conservative. So this quantifier-free correctness is a very small fragment of this conservative. And now the theorem is that quantifier-free correctness can be added conservatively, but if in addition you add the information that all propositional tautologies are true, this is not conservative. Yeah. So we still don't know whether adding the information that propositional tautologies are true. We don't know how strong it is. What we know is that if you in addition add quantifier-free correctness, then we are on the non-conservative side. And indeed, this is another incarnation of CT0. Here the theorem states that this proves DC out, and we already know that DC out is not conservative. The proof of this is a variant of the previous argument. So it's like, again, a Yablo style. We construct a Yablo-like sequence in a bit different manner than before, but perhaps I would say in the same style. Yeah. Okay. The proof. We are trying to derive DC out. So let's assume that we have a sequence of arithmetical sentences. And let's assume that this sequence is a counterexample to DC out. So what does it mean? It means that a disjunction over this sequence is true, but each individual disjunct is false. Yeah. So in effect, for an indirect proof, assume that DC out is false. And now, again, we define a Yablo-style sequence. 5-0 as usual, nothing special, just to start the machinery running. And 5k plus 1, this is really what is important. With an implication, the antecedent states that a disjunction of all these alphas up to k holds. Yeah. So we add this suspicious condition in the antecedent. All the and individually they are false, but a disjunction is true. So this is what is suspicious. How can a disjunction be true in such a situation? So let's say that it's true. That's the antecedent. And then the consequent, it states as before, sort of, it states one of the earlier guys, one of the earlier 5 i's false, but we modify it a bit. So this time starts with the central quantifier, there is an x, it's this disjunction. So it's like spelled out would be there is an x such that x is 0 and not 5-0, or x is 1 and not 5-1, or and so on and so on. Yeah, up to okay. So this time it looks like that. And next, similar style as before, we finish the proof by showing, well, 2 things. Firstly, that 5 formula, all of them, that they are true. And secondly, that if the disjunction is true, then some of the 5j's must be false. So jointly, this produces a contradiction. The disjunction cannot be true. Yeah. The first claim, it's a bit more involved than the previous argument because of this central quantifier, and the formula looks a bit different. Yeah, but roughly, that's, in the first part at least, it goes more or less in a similar manner as before. The second part will be different. The first part here, it really does not use propositional tautologies, quantifier-free correctness. Both assumptions are used in the second part of the proof. Here we assume other 5k plus 1 is not true. It must be k plus 1. 0 is a triviality. Then we just spell out what it means. It means that the antecedent then this is just application of this 2k for every x. So for k in particular, maybe I will not go through these details. I will show you the second part. It's more interesting because this is really like the previous proof, only formula is a bit more complex, but nothing so different from the analogous part of the previous proof happens here. Here is something different going on. Because we use here in this part, we use these assumptions. Tautologies are true, propositional tautologies are true, and quantifier-free correctness. Yeah. So for this claim, we argue that if this disjunction is true, then one of the guys below or up to k must be false. Yeah, together with the previous point, it produces a contradiction ending the proof. Okay, so what happens here? So we fix k such that the antecedent of the implication which we are trying to prove holds. So the disjunction of alpha days up to k, assume that this is true. And we know from the previous part that phi sentences are true, in particular phi plus 1 is true. Yeah, phi k plus 1 is an implication which has this antecedent. The consequent is an existential statement. Yeah, so we can instantiate. There is an x such that proves m. In effect, we obtain disjunction. It is true that 0 equals m and not phi 0, or k equals m and not phi k up to k. Now, use quantifier-free correctness. Quantifier-free correctness really permits us to work here. The problem is how to handle long expressions, long conjunctions. So by quantifier-free correctness, we'll have the information that the conjunction of all these expressions, m is not identical to j up to k, with for j which are not m. This conjunction is true. Quantifier-free correctness. Yeah, and then we employ propositional tautology. So if we have this conjunction, we have this, because it's repeated here, yeah, then it follows that it's true that m equals m and not phi m, and we obtain this because this implication is a propositional tautology. Here we employ the fact that propositional tautologies are true. But in order to do this, we need this long conjunction. Yeah. So it follows, in effect, it follows that not phi m is true, which is what we want. Yeah, consequent. So this result, it's as I said, is somewhat the motivation for this was this open question, yeah, whether adding propositional tautologies are true. how strong it is. We are not able, we have not been able so far to eliminate the use of quantifier-free correctness from this proof. So looks like an essential step, but maybe it is not. We don't know. So let me finish, because this is really all. This problem of propositional tautology. So all I can say is that so far it has really proved to be stubborn. I mean, we tried to prove and disprove it. We tried to apply an Ayad-Visser technique to construct a satisfaction class containing propositional tautologies. There was always some bug and several arguments, purported arguments, trying to disprove this also didn't bring effects. So as for open problems, so I mentioned this one. I mentioned earlier that we do not the open problem about term version of CT if we formulate CT minus with a condition for terms instead of numerals, then we don't know how strong CT0 is. There are additional open questions, or at least I haven't seen the answer in the literature. Some of them have to do with this term versus numerals thing. So, for example, imagine, so let's assume that we have, we are trying to compare CT minus with CS minus, where CS minus is an axiomatic theory of satisfaction. Yeah. So it's like the axioms are very similar to the axioms of CT, only we use a binary satisfaction predicate instead of the truth predicate. And the question, what is the relation between the two in the sense of definability? Is it possible to define in CS minus a truth predicate of CT minus? So all I can say is that none of the usual methods seems to work. Some induction is needed to prove properties. I mean, like in the satisfaction theory, you can define being true as being satisfied by some sequence, being satisfied by all sequences, being satisfied by the empty sequence. None of this seems to work in the absence of induction. An analogous question, take CT minus, can you recover in CT minus a satisfaction predicate? Sort of. The answer is, yeah, well, depends. If your version of CT minus, if it is a numeral version, you can. If it is a term version, we don't know. So just these examples, and I think I should finish.
Okay, thank you, Cezary. Let's all think. So we can take questions. Before I take questions, I can actually respond to Roman's question from before, because before I take questions, I have an answer, if you don't mind. But Roman asked a question earlier about essentially the piecewise coded portion of the truth predicate versus the disjunctively correct part. And So I'll just say this is essentially the Anayat-Pakhamov proof that DC is equivalent to delta knot induction. I don't know if Roman is still there. So
no, I'm here. I'm listening.
Okay. Yeah. So this is essentially the same the proof that that Ali and Fyodor had. It was so if you look at their paper, it's section 4. It's very readable. It's
right. No, right. No, but maybe I was but that's so. Well, if this is the proof, that's fine. But now, if you know that in delta zero induction fails, well, the question is how badly it fails. Because if a set is not satisfying delta zero induction, that it stops being piecewise definable from certain point on. All standard parts are piecewise definable and maybe a little bit beyond. So I just wondered, if you ask a question, what is the shortest disjunction for which disjunctive correctness,
so,
where is it? How is it something that you can see in this Pakhamov and Ayat proof?
What you can recover is that essentially there's a couple the modules some things that you need, but that if you have disjunctive correctness up to disjunctions of length C, let's say, then you have then you can code the truth predicate up to C.
Right. So that answers my question then.
Yeah.
Right.
So certainly the other way around, if you have a failure of it being a class, then there's a failure somewhere below. So I apologize for hijacking that for a second, but I did have an answer to that question, so I wanted to get that in first. But are there any questions for a speaker?
I have a naive kind of question.
Go ahead, Ken.
You can't see me though, right?
I cannot see you, but
my video is screwed up. Sorry about that. In the abstract, you mentioned that you had to look at disjunctions which might be infinitely long, might have non-standard length.
Yeah.
But in the talk, it seemed that the number C was always a finite number, that I didn't see any non-standard.
Okay, no. So let me move back perhaps to the, you are still seeing my presentation?
Yeah.
Okay. So let me move back maybe to this first.
Good.
I think you had it earlier, or I think you had it earlier. In the slides, even before this, before sequential induction.
So I sort of, I suspect that I understand why you thought that this is, we consider only finitely many disjuncts, because there is a certain, this trick with bracketing here. So all these principles are characterized in terms of a disjunction over sequence of sentences S, where S is arbitrarily long. Yeah?
Okay. Yes.
That's the definition. However, what was used, in fact, several times in the proofs, was this fact due to the choice of the bracketing. Bracketing is grouped to the left. So it's like when you have a long disjunction, like this is a long disjunction, there are two parts. This is the main connective, the left disjunct is a long disjunction. The second disjunct is simple, and several times, a couple of times in the proof relied on the fact that our disjunctions are bracketed in this way. So, for example, typical point was that if such a disjunction is not true along disjunction, then we can infer that phi c, yeah, a concrete element of the sequence. It's not simply by the compositional axiom for disjunction. It's like, it might look like we are working with these finite pieces, but this is because of the bracketing. Yeah. Incidentally, let me add that our paper contains also the information that, in fact, for DC out, for the non-conservativity of DC out bracketing, the way of bracketing is important. With some other ways of bracketing, DC out will be conservative.
But when you wrote alpha 0 ... alpha c, could c be non-standard?
Yes, absolutely. Yes.
Ah, okay, good. Thank you.
Yes, I would say C has to be. I have a small comment and one short question, if I may. Cezary, because one comment is about, at some point you had this digression about the philosopher who would object to this strength of CT. So now with induction, and then the argument for that was, look, no, come on, induction is an arithmetic axiom, but I think that there are certain responses to that, because induction on its own is not really arithmetic. It's just the statement about the omega being the least infinite, ordinal number. It's a statement that somehow you can reach every number from 0 by applying the successor relation that's definable in the ordering. So it's very weak. It's not really arithmetic there. It's just a vision of what natural numbers are. And if you talk about theories of truth, then what's hidden in them is that you're talking about a formal language. And there you also make this assumption that every formula is generated from some set of basic formulas, atomic formulas, in a finite number of steps. It's already in the whole setup of the question. There is induction already there implied. So no, this doesn't undermine any of this investigation of strengths of various forms of the induction axiom in the non-standard case. But this argument that the induction is arithmetic is really, but it's not really. It's sort of too crude to make the argument. So this is just a short comment. But the other question is that you mentioned at the end the role of the numerals in the quantifier axioms. So, and you mentioned that there's this question whether CT, in models of CT minus, you can define satisfaction, or whether you can define inductive satisfaction. There is this result of Bartosz that that allows you to define some partial inductive truth definition from a full one, not necessarily inductive. But are you saying that Bartosz's proof uses the numeral version rather than term version of the
I'm not sure what he used. I would say most typically we work with the numeral version, so it's quite probable that that it is used.
So that's interesting, and it's specific. It's already at the level of just arithmetic, not any extension of the language of arithmetic, just arithmetic terms. I see.
Yes.
Okay. Thank you.
So at least I haven't seen the answer in the literature. Okay, to formulate it cautiously. As for your comment, So this was based really, as far as I remember, on the observation that when you have this extended induction axioms, say for T predicate, that you could replace the T predicate with an arbitrary other predicate, and induction would be just as acceptable for this other predicate as for T. And this in contrast to these truth axioms. When you replace truth with something else, the axioms can become false. Yeah, this is not so with induction. So that was the difference with these people. Well, I do not have to say these people. I can say clearly, hard refilled. Yeah.
I see. Right. No, but I think that there is no, but I think this is an interesting opening for a whole discussion about the role of induction and how arithmetic, because I was only commenting on the sort of role of arithmetic. In the sense, arithmetic begins once it's really plus itself is not enough. You need plus and times, and then the strength of induction together with arithmetic axioms allows you to the arithmetization of the language and this and that, and the whole power of the thing goes from Gödel up. But induction on its own, it's very weak. It really depends on the language. So the base theory matters much.
Yeah, I agree, and I definitely agree that it's an opening. Yeah.
Okay. Other questions?
Yeah, I can see that you can go from the numeral version of CT minus to a satisfaction version, even if it's slightly more subtle than you would suspect, I guess. And what about from the satisfaction version to the numeral version?
What about from the satisfaction theory? Yeah.
Yes, we start with the satisfaction theory. Can we also?
We don't know this. Yeah. So my suspicion is that you need some induction to recover, to define the truth predicate in a bare satisfaction theory with no induction. Yeah.
Right. Yes. Because the point is, of course, that substituting a numeral could do, if you have the satisfaction version, the substitution of a numeral could do something crazy, right?
Yeah. It's as I said, all the usual ways of defining truth from satisfaction do not seem to work in such a context, and perhaps the reason is that nothing works. But an argument would be needed for such a general claim.
And a philosophical question then maybe. So, because the truth predicates with the numerals and the terms, well, I mean the truth series with the numerals and the terms for truths seem to be really dependent on that you have arithmetic, right? Where you have for every object you have a term. And so as soon as you start looking at set theory or whatever other theory that has numbers but also other objects, you're forced to use satisfaction. So wouldn't that be an argument that satisfaction is the more fundamental notion, and that one should do all this work for satisfaction in the first place?
So two comments to this. Firstly, I would say that satisfaction either with some induction or with some additional axiom which permits us to recover the truth predicate. Because when we use satisfaction theory, we would like this theory to permit us to discuss truth also. Yeah. So probably bare compositional clauses have to be supplemented by something. This something can be either induction, but not necessarily. You can stipulate some reasonable behavior of satisfaction predicate, add an axiom which add induction could prove, and truth theories in the context of set theory. Kentaro Fujimoto, yeah, he wrote some papers on this. And what he's doing, he's working in the language of the model, yeah, expands the language, yeah, and then working even as a theoretic setting, he can use truth as primary without the detour of satisfaction. But the cost is you could say somewhat artificial change of language.
Yes.
To put it mildly.
I believe. Yeah, well, my theory is that the whole thing really rests upon a misunderstanding. So there's in logic we use the word sentence for closed formula. And I think that's not a correct analogy, right? So the sentences in natural language are much more like open formulas with words like he and it, etc. Than they are like sentences. And so the notion of satisfaction really should be the fundamental notion. And it's so there's a kind of philosophical misunderstanding that makes people think that truth should be the fundamental one. Well, that's a different discussion. So maybe, do we still have time for one small question?
Yeah, go ahead. No question.
Okay. Yeah, so I think we talked about this before. So if you look at the disjunctive correctness, so you could have things that are consequences of it, but are still weaker, right? So for example, we could have simply an axiom that says that all rebracketings of, so if one bracketing of a disjunction is true, then all rebracketings of it are true. And you could also throw in permutations of the disjuncts, so that you really are saying that a disjunction is really a disjunction of a set, or of a multi-set, or whatever.
The principle that propositional tautologies are true would give you all the rebracketings.
Of course, yes.
Yeah. So,
but not the other way around, I guess, right? Or does it?
What do you mean?
So if we simply stipulate, if I simply have an axiom that says the truth of the disjunction is really insensitive for, let's say, the order of the disjuncts, the multiplicity of the disjuncts, and the bracketing of the disjuncts, right? If I simply have that axiom, So
yeah, so
that's weaker.
yeah.
That's weaker than the proposition. At least prima facie weaker than the proposition.
Yeah.
Tautologies, but it follows from disjunctive correctness, but it's not.
It's not equivalent.
It's not.
It's not equivalent.
At least prima facie.
Yeah, probably not.
I think this is in your paper, Cezary, with Bartek. This is you take the disjunctively trivial models, the model which every disjunction of non-standard length is true. I mean, most likely you have to do some work to show that re-bracketing will. Well, but you know, if every non-standard disjunction is just true, this can be added conservatively.
Right. Okay,
so,
yes, you're right.
Yes.
A good point. Yes.
So
I forgot about that.
all these non-standard length sort of truth principles are have lots of pathologies that Bartek and Cezary and them have exploited quite a lot.
No, Ali and I already knew about
yes,
that.
absolutely. Yeah.
I completely forgot it again. Thanks. Good.
Okay, so let's thank Cezary one more time. This is a great and very interesting discussion after.
Thank you.
So this is what I said. This is our last meeting of MOPA for this year, and we are planning to have meetings again in January, where Albert will be speaking. I think you're the first speaker in January. So we'll be meeting again January 10th, and then we'll go from there. So definitely get on the mailing list if you would like to sort of stay informed of the meetings. Okay, so have a happy New Year and happy holidays, and I'll see you
happy
all.
holidays.